Okay, in this podcast we're going to look at, oops, mouse is going crazy. Alright, we're going to look at molecular geometries. Again, a lot of this we had in Honors Chem, but some of it is new. And I don't think you're going to find it to be very difficult. So let's go ahead and get started. Okay, so what determines the shape of a molecule? Well, if you remember from last year, what we said was that electrons here and electrons here are going to repel each other. And electrons here and electrons here. Because they're all negative, they're going to repel other pairs, and they're going to be spaced as far apart as possible. Okay? So whether they are bonding, as in the case of the NH, or their lone pair, they are going to repel each other, and therefore space themselves as far apart as possible. And this will allow us to predict the shape. Now remember, when we think about the shape, we want to think about how many places around the central atom we have electrons. And we call those electron domains. And it doesn't matter whether it's in a bond, or whether it's a single bond, or a double bond, or a triple bond. They count as one domain. And lone pairs also count as one. So here we have 1, 2, 3, 4 domains around the central atom. Okay? So the valence shell electron pair repulsion theory, also known as VSEPR, is the theory that leads us to these shapes. So what it says is the best arrangement around the central atom is based on the maximum separation of electron pairs to minimize repulsion. So valence shell, so we're talking about valence electrons that are involved in bonding, electron pairs, and it's the electron pairs around the central atom, and it's all about them repelling. So that's what VSEPR is. Okay. So these are 6 different geometries, all of which you're going to need to know. Actually, there's 5 different geometries for electrons, where there's 2 domains through 6 domains around the central atom. Okay? And in all cases, what you'll see is if there's just 2 domains, they're going to be equally spaced apart at 180. If there are 3 domains, they're going to be equally spaced apart at 120 degrees. In a 3-dimensional space, for 4 domains, will be equally spaced apart, and so on and so on. Okay. So all we need to do is count the number of electron domains. And in this case, we have 1, 2, 3, 4. Those electron pairs are going to be equally spaced apart. So the electron geometry here is tetrahedral. Even though there's no atom up here, there are lone pairs which also take space just like they do here. Okay, so the electron geometry is tetrahedral. The actual shape is not tetrahedral. Okay. So molecular geometries then depends on VSEPR, where the electrons cause this, are located so that it causes this separation of pairs. And then the molecular geometry depends on where the atoms are. So even though I have a lone pair here, there's no atom sitting up here, so this ends up becoming trigonal pyramidal. So I still have these same separations of these 4 pairs, 1, 2, 3, 4, but because there's no atom up here, I do not have a tetrahedral molecular shape. So molecular geometry is defined by only the atoms in the molecule, not the non-bonding pairs. So within each electron domain, there might be more than one electron geometry. So if I have 4 domains around this central atom, it's possible I have 3 different, they're all electron geometries are the same, but the actual shape of the molecule is going to be different based on whether or not these are lone pairs or bonded pairs. So if I have a bond with an atom on each of the electron domains, I have a tetrahedral shape, equally spaced apart. if I have one lone pair and only 3 atoms attached, I'm going to have trigonal pyramidal. This nitrogen is going to be sticking up. And if I have 4 domains around the central atom, but 2 of those are lone pairs and not bonded pairs, then I will have a bent shape like I do in water. Okay, in a linear electron domain, there are 2 locations and two locations of electron domains, and they're each going to have a bond. And so the electron geometry is linear, and if I have single bonds and there's no lone pairs, then I'm going to have molecular geometry of linear. Okay. Now remember, so in the linear domain, for the electron domain, there's only one molecular geometry, which is linear. Okay, so whenever I have just 2 atoms, so I have HCl, or H2, or CO, carbon monoxide, it will always be linear. It's the only choice, right? I put a bond between those two. The only thing they can do is be across from each other. If I look at a trigonal planar domain, which is not all that common because I have 3 equally spaced electron domains around the central atom, which means that either I have an exception to the octet rule, like I do with boron trifluoride, where I have boron only ends up with 6 electrons in the central atom, but I've got 3 equal domains here, or I end up with I can end up with a bent shape, or I could also end up with something like let's see, SO3, which is going to end up looking like this. Okay, so this is also going to be trigonal pyramidal or trigonal planar, even though this is a double and this is a single. Remember, these are hybridized and they're all essentially the same. Okay, so there are 2 molecular geometries for a trigonal planar electron domain. It's either going to be trigonal planar or bent if there is a pair of electrons that are not bonded. Okay, so we need to in this course we need to know about bond angles. So non-bonding. So if I have just a perfect tetrahedron, for instance, and I have let's say I have methane or carbon tetrachloride or something like that, these angles are all going to be 109.5, right? Perfectly spaced apart. But if I have something like NH3, where I have lone pair, these are not all 109.5, and that's because the non-bonding pair of electrons, the ones here, take up more space than the bonded pairs. Okay, so these are going to be skewed further away from this lone pair, so they take up more room, and as a result the bond angle shifts. So this angle between the lone pair and the atom grows, and this shrinks a little bit. It goes from 109.5 down to 107, and it loses another 2.5 degrees if I have 2 lone pair, because remember, those lone pair take up more space, slightly more space, so it's going to, in the case of water, my bond angles shrink to about 104.5. Okay, so let me just see if I can erase all this stuff here. Alright. So double and triple bonds place greater electron density on one side of the central atom than do single bonds. So if I have a double bond and 2 single bonds off a central atom, I may have more space here, a larger bond angle, where the double bond is, or the triple bond is. Okay. If I have a tetrahedral electron domain, 4 places around the central atom where there are electrons, I can have 3 different shapes, right? If an atom's attached to each, I'm going to have a tetrahedral molecular geometry. If I only have 3 bonded atoms, I'm going to have a trigonal pyramidal. And like we just said, if we have water with 2 lone pairs, it's going to be bent. Okay, now we can also have a trigonal pyramidal. Okay? And there are 2 different geometries involved in this electron shape. Okay, so if you think about it, I think Renee McCormick explains it this way. If I consider this to be my head and this to be my feet, then these are 180 degrees apart, right? And then if I consider that I've got 3 atoms equatorial around the equator, so imagine I have, she calls it a triangular belt. A belt with a triangle equally spaced apart. If these are equally spaced apart around 360 degrees, each of them is going to be 120 degrees, okay? And then if you think about it, I've got these lines sticking out from my head. This angle is a right angle, and it's going to be a 90 degrees. Okay, so along the equatorial axis, they're going to be 120 degrees apart. Along the, if I compare the axial to the equatorial, they're going to be 90 degrees apart. These 2 here are going to be 180 degrees apart. Okay. So this is obviously, I only have a trigonal bipyramidal if I have an expanded octet, right? So this is going to be the 3rd period and greater. So I have 1, 2, 3, 4, 5 electron domains around the central atom. Okay. Alright. So lower energy results from having non-bonded electron pairs in the equatorial as opposed to the axial. So we're always going to have the head and the foot, but I won't always have the complete triangle in my belt. Okay, so if there's not an atom, it's not going to come from the head or the foot, it's going to come from the belt. Okay, and again, lone pairs take a little bit more space, so that shifts this angle. This becomes a little bit more than 180. This is an interesting position. If you shape, if you turn it sideways, you'll see this is nothing more than a seesaw, and that's actually the technical term for that shape. It's a seesaw. Okay, so I can have if I have bonded atoms at all 5 domains, I have a trigonal bipyramidal, right? So it's a pyramid on top and a pyramid on the bottom, trigonal bipyramidal. If I am missing the one of the equatorial, I have my seesaw. If I have a 2 lone pair, they're both going to come off the equatorial. They're both going to come off the belt, and I'll have a T shape. And if I have only 2 bonds, and I have 3 lone pair, they're all going to come off the belt, or the equatorial position, and I'm going to just have a linear molecule. Okay, so for octahedron, now again, if I have an octahedral, then I have 6 domains around the central atom, and of course this is an expanded octet, and this can only happen if I am in the third or greater. I don't want to say above the 3rd, because that, so it could be 3rd period, 4th period, 5th period. They've got to have enough space. They've got to have d orbitals to allow this to happen, right? So if I think about this shape again, let's say I have atoms attached to all of them. I still have a head, right? I still have feet. This is going to be 180. Now my belt is no longer a triangle, it's a square. So I have 4 equally spaced locations on the belt. Okay, and these are going to be 90 degrees apart from each other, and this is going to be 180 degrees apart. Okay, so if I have atoms on all 6 domains, then I have an octahedron. If I have a one lone pair, I'm going to have a square pyramidal. It's going to be kind of like this. Didn't draw that very well. And if I have a square planar, it's going to be kind of like a Ferris wheel, right? It's going to be all on the they're going to be on the equatorial position. Okay, so if we're talking about something larger than those shapes we've just reviewed, then you generally, when you talk about shape, you have to talk about around which atom. So you have to specify. So if I'm talking about the shape around this atom, I have a tetrahedral shape. If I talk about the space around this atom, I have a trigonal planar shape. Okay, so it depends. These molecules get bigger, and you can't really describe them with just one word. So a lot of times when we're talking about shape of molecules, the shape we refer to usually is talking about what is the functional group that's reacting. Here I have a carboxylic acid, double bonded oxygen, OH, which is going to be the reactive site that reacts with other stuff. So larger molecules we really don't get into naming. Okay, so we talked about bond polarity. Remember, we talked about, let's say HF, right? This is more electronegative, so, I'm going to have a dipole moment, right? It's going to be more electrons around the fluorine than there are around the hydrogen. But we can also talk about dipoles within a molecule. So, So I can have a molecule where I have polar bonds. In this case, carbon and oxygen are polar, right? Oxygen is more polar than carbon, so the dipole goes this way. And I've got the same thing on the other side, the dipole going the opposite way. And the overall dipole for the molecule is 0, and that's because if you add these two vectors together, they cancel each other out. So even though I can have bonds that are polar in a molecule, I can have an overall nonpolar molecule. So this is what CO2 would look like. It's nonpolar. There's no part of this that's sticking out that's going to be more electronegative, that's going to cause it to be attracted to itself. So I can actually show the bond dipoles and then show what happens for the overall. So here I have water. The hydrogen is less electronegative than the oxygen, so my dipole for the bond goes this way. If I add these overall dipoles together, I have a dipole that has the top of the molecule being more electronegative than the bottom, right? So I can show an overall dipole for the molecule. So here I have a molecule. It's only got one bond, and that bond is polar, has a dipole, so the molecule is also polar. Here I have carbon tetrachloride. Each of these bonds is polar, and the dipoles show facing the chlorine because they're more electronegative. But if I add all of these dipoles together, they cancel out. It becomes nonpolar. Here I also have polar bonds, in this case with the nitrogen being the most electronegative. But this is a polar molecule because if I add these dipoles together, the dipole faces that direction. Here I have a symmetrical shape. I have dipoles on each of the 3 bonded atoms. They're all facing the same direction. If I add these three vectors together, I'm going to get 0. So this becomes nonpolar. I can take this same nonpolar molecule here, and I can change one of the atoms, and now I have a polar molecule, because this is chlorine is more electronegative than the hydrogen. So these are smaller. These are smaller, right? And this becomes polar. So if I have a symmetrical molecule, everything's the same on the outside, no lone pairs. I have a nonpolar molecule. It doesn't matter what's on the outside. If I have one thing that's different on the outside, it's going to become polar. If I have lone pairs, I will always be polar, because those lone pairs are going to stick up and they're going to be negative. It's going to cause a dipole. Okay, so let's talk about what happens when atoms bond in terms of their overlap. So when we think about covalent bonds, they form by sharing electrons of adjacent atoms. So here we've seen this diagram where the hydrogen atoms come together, and as they do, they reach this point of lowest energy where they overlap, and we say the electron pairs are there. We can also look at an overlap if I have an s orbital with a p orbital, and then they overlap, do this head-to-head overlap, and I have electron pairs, right? So chlorine would do the same thing with two p orbitals. Okay. So this is the diagram I was talking about. Bonding occurs when I have the lowest potential energy. As I bring these electrons together, these hydrogen atoms together, the energy goes down as they form this pair. And if I get too close, then I start to have the nucleuses too close together and they repel each other, right? Okay. But it becomes difficult to imagine, if I have a tetrahedron, how this overlapping occurs. It's not necessarily this head-to-head overlap, right? So if I have 3p orbitals, I can imagine this, and this coming together. But what happens with these guys? So let's think about methane. Methane is CH4. And it's a symmetrical molecule. There are 4 electron domains around it. So the question is, are all those bonds the same? And you may say, yeah, sure they are, but let's think about where those electrons around the carbon come from. There are 4 valence electrons. 2 of them are s electrons, and 2 of them are p electrons. Now, if in fact I have s and p electrons, wouldn't something about these bonds be different? An s-type and a p-type that combines with the s from the hydrogen. And in fact, these are all the same. And so in order to explain why they're all the same, why they're all the same shape, the same thing happening, we use this concept called hybridization. And hybridization is where atomic orbitals on the central atom mix to form new hybrid or mixed orbitals. Okay, I'm going to take a look at what that means. So these hybrid orbitals are different than the original orbitals. So if I started with an s and a p, when this s and p come together, I'm a terrible artist, aren't I? They are no longer an s and a p orbital, and they are all equal. So if I think about the methane, and it's got hydrogens, right? And I'm talking about these bonds here. And even though 2 of these were s orbitals and 2 were p from the central carbon, what we're saying, in fact, these are all the same. And I'm not going to call them s, and I'm not going to call them p. I'm going to call them sp3s. Okay? So I no longer am calling them s, I'm not calling them p's, but instead I'm saying I have 4 equal orbitals around the central atom, and I'm calling them sp3. And it turns out this number 4, if I have 4 bonds around the central atom, I want the superscripts here to add up to 4. So I've got S is 1, P is 3, so this adds up to 4. So I have 4 sp3 orbitals. So let's take a look at what that means. Now, these orbitals, these sp3 orbitals, are higher in energy than the s orbitals, but lower in energy than the p orbitals. Alright, so if I just think about beryllium, in its ground state, it wouldn't be able to form any bonds because it doesn't have any singly occupied orbitals, right? So I've got a pair here and a pair here. So where's the pair going to be when it bonds? And what hybridization says is what happens is one of these s electrons gets promoted to a p. Okay? And now it has 2 singly occupied orbitals and can form 2 bonds. So the mix of the s and the p orbital yields two, kind of a strange word, degenerate orbitals that are considered hybrids of the two. So that I have an s orbital and a p orbital, and when I form a hybrid, it becomes this strange shape that's got this small piece and this large piece. Okay? And if I have these two together, I've got 2 sp orbitals. So where I had 1 s and 1 p, now I have an sp hybrid orbital. So they align themselves 180 apart. So here's beryllium. It's got an sp orbital, and it can bond with 2 atoms. So this is consistent with the observed geometry of beryllium. It's a linear shape. So the hybrid orbitals for beryllium, when it's bonding, look like this. We don't call them s, we don't call them p, but the bonding orbitals are now these sp. Okay, higher in energy than the s, lower in energy than the 2p. Now boron, which has 3 valence electrons, I can do a similar kind of thing, right? I have 1 p electron for bonding, but I can promote this s electron to be a p. Now I have 3 potential bonding, and rather than calling them s and p, because in fact they're all the same, they're sp2 hybridized orbitals, 3 places where they can bond. And again, 3 valence electrons is going to form 3 bonds, and I have 1 s, 2 p here, so it's 1, 2, 3. It has to add up to the 3, the number of valence electrons. Okay, so I end up with 3 sp2 orbitals, right? And those sp2 orbitals align like this, consistent with a trigonoplanar shape. Alright, so if we look at carbon, carbon, you'd look at this and say it has a 2 2s's and 2 single 2p's, but in fact we know carbon forms bonds with 4 atoms around it, so one of these s's must have been promoted, and rather than calling s and p, we have now 4 sp3 orbitals. This number has to be the sum of this 3 plus this 1, which is 4. So this is what we end up with, right? We end up with 4 sp3 orbitals. Okay, so if we have expanded octet, now we must use d orbitals, right? So I can't go any higher than sp3. So if I have 5 places around the central atom that's being bonded, I need to add a d orbital. And of course, if I have 6 places around the central atom, I'm going to have sp3 d2, because I need 2, 5, and 1 is 6. Okay. So these superscripts again need to add up to the number of bonding pairs around that central atom. So for the trigonal pyramidal with 5 we get sp3d, and for octahedron we get sp3d2. Okay, so here's the shapes, here's some examples. Okay, so we're going to talk now about a different theory that's somewhat supportive, somewhat a little bit different than VSEPR and what we're talking about with hybridization. This is called valence bond theory. And what it says is there are 2 different ways that bonds can overlap to form bonds between the atoms. And those 2 types of bonds are called sigma and pi bonds. Okay, if I have a sigma bond, it is, if I have, let's say, 2 s orbitals, 2 different atoms, it's going to form a sigma bond. If I have an s and a p, it's going to form a sigma bond. So it's characterized by head-to-head overlap. So this atom colliding with this atom, and it's this head-to-head overlap. This S colliding with the head of the P as opposed to the side of the P, or 2 P's hitting head-to-head. So you end up getting a cylindrical symmetry of electrons, a cylindrical symmetry of electron density, okay, around the axis. Pi bonds come from overlapping side to side. So if you imagine, if I have a, let's say, my P, right? I've got 3 P orbitals, and let's say, I'm a terrible artist, and you know that, right? So this is my head-to-head overlap, but if I have more than one bond, it has to come from one of these other P's. And those P's, you know, we're bonded already here on the PX axis, let's say. If I want another bond, it has to come from this side-to-side overlap. Okay? So pi bonds are characterized by side-to-side overlap, and that electron density ends up being both above and below the nucleus of the atoms that are combining. Let's take another look. Okay, so single bonds are always sigma bonds. Single bonds are always sigma bonds because the sigma overlap is greater. Greater overlap with sigma bonds than you have with pi bonds. Because the pi bonds are overlapping side to side, you get less overlap than if you have this head-to-head. Sigma's head-to-head, pi is side to side. This is more overlap. More overlap, less overlap. Okay. If you have a double bond, what you have is one of these is sigma and one of these is pi. If you have a triple bond, one of these is sigma and the other 2 are pi. So within a bond, doesn't matter if it's single, double, or triple, there can only be one sigma. And then if you add a multiple bond, they're going to be pi. Okay, so in a molecule like formaldehyde, CH2O, we have overlapped in the sigma, right? So we have this nice, neat overlap. But then the pi bonds also overlap, and when they do, we get this overlap side to side that makes it look like this, I don't know, dog bone, right? So the overlap is in a pi fashion when that happens. So we have a triple bond. The center one is the head-to-head, and that's sigma, and then if I add additional orbitals, or additional bonds, multiple bonds, they are pi. So sigma bonds themselves are stronger. Sigma is stronger than pi, but of course a single bond is weaker than a double, because this double is a, whoops, I'm having trouble writing my sigmas. My double bond is a sigma plus a pi, right? So of course this is stronger than a single. But sigma bonds themselves are stronger than pi's. Okay, so that's sigma and pi. Just a little piece there. Now we want to talk about what happens with resonance. So we talked about resonance when we were drawing Lewis structures, and we said that when we have resonance structures, no one structure itself can explain the molecule, and you need to have these brackets and show multiple structures, because the double bond can be on any one of those three atoms. But in reality, what you have is each of the four atoms has a p orbital, and the p's overlap on all three around the central nitrogen. So the pi electrons are not localized between the nitrogen and one of the oxygens, but they're delocalized all the way around. So these you can consider them to be moving, right? So I have this whole plane above the nitrogen and oxygens, and another plane below where the electrons are delocalized. When we talk about resonance, benzene is a popular topic, and we talked about this when we talked about Lewis structures. And remember, benzene has 6 carbons with hydrogens attached, and they have double bonds between every 2 carbons. And often the shorthand shows like this. But if you were to look at the hybridization, what you have is you have, side to side, 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 and side to side. On the top, you have the same thing, side to side, side to side, side to side. So in fact, what you have is you have, basically 2 circles with the carbons in between, right? So you have these 2 spheres of delocalized electrons moving around above and below the atoms. Like this. This is what it actually ends up looking like, right? You have basically a double ring of electrons with the atoms in between. And this structure makes benzene very, very stable. Okay, so we're going to stop there.